Alright, silly people, here's the situation. We're going to be using the relaxation method to solve the equation x equals 1 minus e to the minus cx, right? Where c is a known parameter and you have to solve for x, right? So um, this is pretty explicitly covered in the book. Um, if you just read he literally writes a code that uses the relaxation method, and so I'm heavily basing mine off of that. But this is going to be end up looking a lot simpler to what he did, right? But the function that we're solving is f of x. It's going to return 1 minus e to the and better do numpy exponent minus c star x. The error calculation in the relaxation method is actually based on the derivative as well as the function itself. So also I'm going to define a derivative of the function, and it's nice because you can very easily do this derivative analytically. In the future we might not be able to do that, but the derivative of that is minus c star x. It's c times e to the minus cx, right? Easy derivative. So with the relaxation method, you start with a guess of what the solution is going to be. I'm going to use 1 for these. Also better define what c is. C is equal to 2 according to part A. You start with an accuracy that you want to have in mind. So I'm going to say accuracy is 1e minus 6, which is what, again, Newman suggests. And we also start with an initial value for the error, which you can just make anything. I'm going to make it arbitrarily large. I always just use Avogadro's number for that sort of thing. Then you start a while loop. While error is greater than your accuracy, the first thing that you're going to do is you're going to make x1 equal to f of x1, effectively updating the value of x1 by making it equal to the function call of that. Simultaneously, you're going to store the old value of x1 in a variable called x2. So I'm just going to put a comma x2 here, comma x1, so you're switching the values back and forth. At this point, you can calculate what the error actually is on this. So error equals, and the way to calculate the error is x1 minus x2 divided by 1 minus 1 over the derivative evaluated at x1, right? While you're going, I guess for this case, you can just print the values as we go, and the last one will be the most accurate one. So we'll just give it a run. I think this should go. And yeah, it starts off at 1, but then it immediately goes to 0.86, and it just keeps on going down until it reaches the actual solution of the equation, which is 0.7968. So yeah, it works. It's pretty easy to use. The next bit of the problem is to, instead of doing a specific value of c, you go on a continuum of c values from 0 to 3 in steps of 0.01. So let's create a c list, which is going to be an numpy a range object from 0 to 3, steps of 0.01. And all of this stuff afterwards is going to be in a loop for c in c list. I'm just going to tab all that stuff forward into the loop. Let's go ahead and also create a output list to store the solutions. And after printing, I'm not going to print line actually, after doing the error loop, just going to have xls be appended with the solution x1 at that point. So after that, it should run, and we can just plt it on plot CLS versus XLS, and we can see all of the solutions in that domain. So it looks like that. So you'll see that it has only the trivial solution of x equals 0 all the way up until you see this x equals 1 guy, and then you can have non-zero solutions. Yeah, okay, if you plug in anything that's less than 1 in x, then e to the minus c times that value is going to be a really big number. And so 1 minus that value ends up being a negative number, but you put in a positive number to start with. So there's no solution for that except for 0. But then when you get to values greater than 1, then e to the minus c times that number is now kind of small, and so 1 minus that number is positive, and so you can get non-zero solutions for it. And so that's called the phase transition. There's a special name for this one in particular. I think it's called the epidemic threshold. You can read up on that in the book. But yeah, relaxation method.